In the name of Almighty God, I'm Mahsa Sankoshi, and today I want to talk about particle tracing module. The particle tracing module is a general-purpose tool for computing the paths of particles as they move through a geometry and are subjected to various forces. The simulated particles could represent ions, electrons, cells, grains of sand, projectiles, planets, stars, and much more. Most of the physics interfaces in quantum multiphysics use the finite element method or FEM to compute fields such as temperature, fluid velocity, electric potential, concentration, or displacement. In contrast, particle tracing provides a Lagrangian description of a problem in which the particles are treated as a discrete entities that can interact with external fields, with boundaries in the surrounding geometry and with each other. Their trajectories are computed in the time domain and by solving a set of equations based on their laws of motion. The most common such system of equations are the second-order ordinary differential equations based on Newtonian's second law of motion, to which the forces based on the external fields can easily be added. As particle travels through the geometry of a model, they may also come into contact with boundaries in their surroundings. When this happens, each surface can affect the particle behavior in a different way. The built-in particle boundary interactions include different types of absorption and combinations of diffuse and specular reflection. The particle tracing module also offers a wide variety of release mechanisms to control how the particles are inserted in the geometry. After the simulation is complete, many dedicated tools for visualizing particle motion and reporting particle statistics are available. For example, here we have a fluid velocity field in the left section of this figure, and in the right section you can see the particle trajectories. A basic particle tracing module usually involves first solving for some fields such as a fluid velocity field for left side, and then tracking particle in the field using forces such as the built-in indirect force right side. Main subject area. Particle tracing module applications can be loosely categorized into three subject areas. The first is charged particle tracing, the calculation of ion or electron passes under electric, magnetic, and collision forces. The next one is particle tracing in fluids and the tracking of microscale particles such as cells or airborne contaminants under the influence of drag, gravity, and other field forces. And the third one is mathematical particle tracing, the setup of customized equations of motion, including the Hamiltonian and Lagrangian formulation from classical mechanics. These three subject areas correspond to the three main physics interfaces included with the particle tracing module: the charged particle tracing interface, the particle tracing for fluid interface, and the mathematical particle tracing interface, respectively. In addition, several multi-physics interfaces are available, each with defined couplings to other physics interfaces such as electrostatics and laminar flow. You see in this picture locations of a particle tracing physics interfaces in the model wizard. The options shown are available with licenses for computer multiphysics and the particle tracing module depending on other licensed products. The model wizard may include options other than those that are shown here. Physics interface guide by space dimension and preset study type. The particle tracing physics name, and another physics name is particle field interaction, non-linearity physics, and for two-dimensional asymmetric, two-dimensional, symmetric, and three-dimensional. And for available study type, bidirectionally coupled, particle tracing, and time-dependent. For a physics interface, particle field interaction, relativistic, two-dimensional asymmetric, two-dimensional symmetric, and three-dimensional symmetric, bidirectionally coupled, particle tracing, time-dependent. And charge particle tracing with CPT, two-dimensional asymmetric, two-dimensional and three-dimensional symmetric. And the name for the available study is bidirectional coupled particle tracing, time dependent. The section of fluid flow particle tracing are such as particle tracing for fluid flow, for two-dimensional symmetric and three-dimensional symmetric, and two-dimensional asymmetric, and available study type is bidirectional particle tracing, time dependent. And fluid particle interaction, two-dimensional asymmetric and symmetric, and three-dimensional symmetric, and bidirectional particle tracing, time dependent. And droplet sprays in fluid flow, which has a bidirectionally coupled particle tracing, time dependent, and the type is two-dimensional type, asymmetric, and two-dimensional symmetric, and three-dimensional symmetric. Mathematical particle tracing is that two-dimensional, asymmetric, and symmetric, and three-dimensional bidirectionally coupled, provide tracing, time dependent, and so on. What about the charged particle? The charged particle tracing interface is found under the ACDC branch in the model design. It is primarily used to trace ions and electrons under the influence of electric and magnetic forces. The electric and magnetic forces can either be entered explicitly as user-defined expressions or computed using another physics interface. The magnetic force can also be taken from built-in data for Earth's magnetic field. Included in the electric force and magnetic force features are built-in options to modulate and AC fields. In this way, it is the way to include a combination of stationary and time harmonic forces in a single model. Monte Carlo collision modeling. In addition to electric and magnetic forces, energetic ions and electrons are often subjected to the collisions with the molecules in a rarefied background gas. At sufficiently low pressure, these collisions can be modeled statistically using a Monte Carlo approach. In each time step taken by a time-dependent solver or at random intermediate times, such model particle has a chance to collide with a background molecule and scatter in random direction. The collision probability and the probability distribution function of scalar particle velocities are based on the particle kinetic energy, type of reaction, background gas density, and collision cross-section data. Because the collision cross-section is usually a non-trivial function of energy, it is common to load a cross section data from a separate file and use it to find an interpolation function. Some of the built-in collision types can release secondary particles of the same or a different species. For example, ionization reactions can lead secondary electrons, and charge exchange reaction can yield a new combination of ionized and neutralized species. Because of its Monte Carlo collision modeling capability, the charged particle tracing interface is something extremely useful in modeling in the motion of the neutralized species, not just baryon or electrons, in spite of the interface of the name. Multiphysics interface for a particle field interaction, which I will describe it later.